Our first speaker today is Galen Bergsten. Galen grew up in the Chicago suburbs before moving to Salt Lake City to earn their bachelor's degrees in plant ecology and astronomy at the University of Utah. They are now a PhD candidate at the Department of Planetary Science at the University of Arizona and are currently in Pasadena on a visiting graduate fellowship at IPAC and Caltech. Galen is also highly involved in service work to help improve diversity and inclusion within astronomy and planetary science. They serve on several committees and working groups, including chairing a working group within the Awesome SAG, and lead several projects to improve the accessibility of astronomy education. The title of their talk today is Demographics of Earth-Sized Planets in the Habitable Zone, from Kepler to the Habitable Worlds. And with that, Galen, go ahead and share your screen and take it away.
Right. Greetings, everyone, and thank you, Tiffany, for the introduction. My name is Galen Bergsten, and I am a grad student at the University of Arizona. Today, I'm here to tell you all about Earth-sized planets in the habitable zone, giving us a better feel for how many planets like Earth there might be, and how many we can hope to find signs of life on. And then in the second half of today's session, Michaela will tell you all about some of those signs of life that we might pursue. So we've got a little synergy going on today. I've added this tagline from Kepler, a mission that tried really hard to find Earth-sized habitable planets and didn't quite manage, to the Habitable Worlds Observatory, an upcoming mission that will hopefully find a whole lot of them. To understand the link between those two missions and get a better feel for how many Earths there might be, I want to start by talking about planet occurrence rates. This is a fancy term for the frequency of planets, usually a particular type of planet, sometimes around a specific type of star. For example, the occurrence rate of hot Jupiters is about 1%, so you could find one hot Jupiter around 1 out of maybe every 100 stars. The occurrence rate of Earths in the habitable zone is usually given this symbol of the Greek letter eta and then the subscript Earth, or eta Earth, and the value of this parameter kind of depends on who you ask. Here is a range of recent literature estimates for the occurrence of Earths in the habitable zone. The horizontal axis is showing this parameter, but normalized by people's different definitions for what is the habitable zone, what is Earth-sized. The important thing is that there's about 2 orders of magnitude here. There are some parameters that are kind of small, on the order of a few percent, so maybe Earths are as rare as those hot Jupiters, and some values that are a lot larger, on the order of maybe 100% or more, which in this case would mean having multiple Earths per star. I'd like to draw your attention to the value up top, what I've labeled the HWO predecessor concepts, which loosely refers to things like LUVOIR and HABEX, these mission concepts that went into the Astro 2020 Decadal Survey, which then led to the Habitable Worlds Observatory. Those works used a value of about 24%, so 1 in 4 stars could host an Earth-sized planet in its habitable zone. But it's not the only number that's on this plot. There's quite a range of estimates, and a lot of the more recent ones tend to be on the smaller side, with an average of somewhere between maybe 10 and 15%. So where does that difference come from? And indeed, where do any of those estimates come from? Well, to explain those points and introduce some estimates of my own, I'd like to break this talk up into 2 parts. First, I'll be focusing on sun-like stars, things that are roughly a solar mass, our F, G, and K spectral types. And then I'll shift gears and talk about M-dwarfs, a group of stars that are smaller, cooler, and lower mass than our sun, but also a lot more common. To talk about either of those things, I first have to introduce the Kepler mission. Kepler was an orbital space telescope trying to find planets using the transit method. This cartoon shows an example where a planet passes in front of a star, blocks out a little bit of that star's light, and tells us, hey, there might be a planet here. Now, to date, we know of about 5,600 exoplanets, and around half of those were first discovered using Kepler, which is kind of incredible. Here's a distribution of Kepler's confirmed planet sample, with the vertical axis showing the planet radii, or their sizes, and the horizontal axis showing their orbital periods, sort of a proxy for how far away things are from their stars. I'd specifically like to call out things that are at 1 Earth radius and 1 Earth orbital period, or Earth-like planets. you might note that there is nothing there because Kepler has no planets that are reliable confirmed detections with exactly Earth's parameters. So that's kind of troublesome. Does that mean that Earths are rare? Well, not necessarily. Consider Kepler's survey completeness, or the mission's sensitivity to planets at particular combinations of periods and radii. By the time we get to planets as small as Earth, and at such large orbital periods as a sun-like star's habitable zone, Kepler could maybe find one in about 10,000 planets, which are not great odds. So it's not necessarily that Earths are rare, but rather that they might just be really hard to find. Well, if that's true, and we don't have any information for exactly Earth-like planets, then where did all of those estimates that are based on Kepler data actually come from? In truth, the vast majority of them are based on Kepler's close-in planets, things at 10 days or 100 days, where there are a lot more Earth-sized planets to work with. As a demonstration, on this plot, I'll show you the planet frequency or occurrence rate of, in this case, small planets, things between the size of Earth and Neptune, as a function of orbital period. And on the right side, I've included some habitable zone boundaries for reference. So I'll start by tossing up, the information that we can actually measure as a function of period, maybe going 1 from 10 days. There's this sort of increase as planets get more and more common. Then perhaps it kind of flattens out, but the information really cuts out at around 200 days where there's just not a ton to go off of. So maybe you use the distribution of these occurrence rates to fit a kind of model that matches that shape. And then you could use that model to extrapolate it across the habitable zone. This way, you could at least make a prediction for how common Earths in the habitable zone should be. And indeed, this is the vast majority of those estimates. They're based on models fit to some version of the Kepler sample with some different cuts and qualities and model shapes to get all sorts of different estimates. But all of this must make one fundamental assumption. Extrapolations require that the place you are extrapolating from is similar to the place you're extrapolating towards. In other words, that these two populations where you have and don't have data are similar enough that you can kind of just keep drawing your line in that direction and nothing really changes. Naturally, that kind of breaks down if there is a difference between those two populations. Say that there was something that affected the close-in planets, but did not affect the habitable zone. Unless you accounted for that difference somehow, your extrapolation might lead to an inaccurate estimate. Obviously, I wouldn't set up this demonstration if I wasn't about to introduce one of those differences. So let's talk about atmospheric mass loss. This is kind of a catch-all term for a process in which planets lose parts of their atmosphere. There's a number of ideas for how that actually happens, but the general trend is as follows. Say that you have some planet with an internal core that is surrounded by a really puffy atmospheric envelope. And that core plus atmosphere combination is large, a couple times larger than Earth, maybe a little bit smaller than Neptune, so you might call it a sub-Neptune. Well, if that planet is orbiting close to its star, say within a few days, it's probably receiving a lot of high-intensity stellar radiation, which could drive the escape of that atmosphere over time. So in a really extreme case, maybe you lose the whole thing, and you'd be left with just that remnant core. Now, that core is smaller than the full planet when it had its atmosphere, small enough that it might now be just a little bit larger than Earth or a super-Earth. This poses a problem for transits at Kepler because we don't know the entire evolutionary history of these planets. What we're really measuring is just their size as we see it today. So you could find a super-Earth-sized object, and it might be one of these remnant cores from a shrunken sub-Neptune, but it could also be an intrinsic super-Earth, something that started that size and has always been that size. For example, a primordial population of rocky planets. So in a sense, these remnant cores might be contaminating that intrinsic super-Earth population. But not every sub-Neptune is going to lose its whole atmosphere. As we move farther away from the stars, these planets are getting hit with less of that stellar radiation until you get far enough away that maybe you don't lose any at all. Perhaps you are retaining all of your sub-Neptune atmosphere, so you're not really shrinking down, and thus you don't have to worry about this contamination problem. Now we have an issue, which is that the habitable zone is far enough away that it probably resembles the right side of this cartoon, that things are beyond a couple hundred days, sub-Neptunes really aren't shrinking, so we aren't producing these remnant cores in the habitable zone. But all of our models and estimates that we're using to predict the habitable zone are based off of the close-in population, where this process is maybe a really big deal. So unless we have some way to correct for that, our estimates for the habitable zone wouldn't look like what we actually expect to find with those sort of intrinsic super-Earth rocky planets. To correct for this, we introduced the magic of fractions. And this plot will ask the fairly straightforward question, how many of the small planets are super-Earths? In other words, what fraction of the small planet occurrence rate is contributed by things that are maybe 1 to 2-ish times the size of the Earth? And we'll look at that as a function of orbital period. So up close, we find that fraction is really high, maybe on the order of 80%. So 80% of small planets are super-Earth-sized things within a couple days. But as we start to move farther and farther out, that fraction gradually starts to drop down until it maybe plateaus closer to 40% out at 100 days. We interpret this as follows. At 100 days, what we're seeing is that intrinsic, maybe primordially rocky population of planets. That makes up about 40% of the small planets. The remaining 60% are these sub-Neptunes, which aren't shrinking down. But as we move closer to the star, we're stripping more of those sub-Neptunes, so we tack on an extra 40% from these remnant cores. Now, for our purposes, the thing that's really interesting is the stuff on the right. We can take that primordial rocky planet population, which is what we expect to find in the habitable zone, and use that component to inform our models and provide a new estimate. The value that we find is on the rightmost side of this plot that has a handful of some recent estimates. And we get a number around 10%. So 1 in maybe 10 sun-like stars could host an Earth-sized planet in its habitable zone. To help put that in context, here's that value from going into the Astro 2020 decadal. Now, yes, the median value is a little bit higher. So at face value, you might think, gosh, perhaps we are finding less planets than we originally thought. I want to mention the point that the people writing those precursor concepts definitely knew that Eta Earth was not like a super solved or well-known problem, and that there were uncertainties on those numbers. And so those uncertainties carried through in things like their yield calculations. So there was a world in those precursor concepts where maybe these missions only find maybe 10, 15 planets looking at 100 stars. I also want to iterate that that was maybe supposed to be like a bad case scenario, like pessimistically, if we get kind of unlucky and the occurrence rate is 10%, we'll find this many. But now our estimate, along with some of the more recent ones, are saying perhaps that's not the worst case scenario. Maybe that's just what it is. Like maybe that is the median value for this parameter. I also need to iterate that this is by no means a solved problem. There are so many moving parts that make Eta Earth calculations so difficult and so non-standardized. There's a lot of effort going into both perfecting our models of this and also trying to understand what all of those little pieces do. While our estimate might be one of the more comprehensive ones to date, there's definitely some stuff that we didn't consider, like the presence of stellar companions. Planetary systems, a good chunk of them probably have more than one star, and that introduces a whole lot of complications when it comes to detecting and characterizing these planets. To illustrate one example, let's go back to that cartoon of a planet passing in front of its host star and blocking out some of its light. There's that change in brightness, which we use to measure the size of these planets. But to complicate matters, say that there was another star in the picture. Now that star is contributing some of its own brightness, which maybe isn't being blocked by that transiting planet, and so the total change in brightness is going to be a little bit smaller. We say that the transit signal is diluted in this sense. And because it's a bit weaker, the planet radius that we would measure is actually going to be smaller than what the true planet radius is. This presence of unresolved stellar companions and radius misestimations is very much a studied problem. A lot of folks have looked into this and worried about it, and it's really hard to do so. But if you want some good examples, I'd recommend checking out the work of Elise Ferlin, and specifically in the context of Eta Earth, definitely check out the work of Kendall Sullivan. Or maybe stay tuned for something that we're cooking up. David Ciardi and Jesse Christensen ran this imaging survey on a control sample of Kepler stars and, unsurprisingly, found some stellar companions that would have been unresolved within a Kepler pixel or two. So as part of this fellowship at IPAC, I've been working with this companion data set, trying to characterize the distribution of radius correction factors. In other words, if there were planets to orbit some of these companions, how off would our measurements of their radii be? And the answer is it's kind of a substantive problem that on average, about a fourth of the stellar companions would need corrections of like 20% or more. That might not sound like a lot, but know that this is kind of a big deal when you have an occurrence rate model that is data limited and thus pretty sensitive to small changes in planet radii, i.e. every Eta Earth model ever made. So our next step in this project is to basically take these companions and then redo the first half of this talk, but now accounting for the fact that there might be some stellar companions throwing off our radius estimates to try and gauge how much of an impact this has on Eta Earth. But that's maybe information for another time. So for now, let's take pause at this little checkpoint and recap the sun-like stars. We found this occurrence signature for their atmospheric evolution, and we used that to isolate this intrinsic population of maybe rocky planets, leading to an occurrence estimate of about 10%. Now I want to shift gears and talk about the M dwarfs, a type of star that are much lower mass and cooler than our sun. I'll adopt a kind of loose definition for things that are like below about 4,000 Kelvin. And M dwarfs generally make up the bulk of stars in the solar neighborhood. They're by far the most abundant things. There's another reason I think they're cool, unintended. Because they're low temperature and lower mass, their habitable zones fall at shorter orbital periods. Now, you might naively hope that this makes it a bit more accessible to probe observationally. Unfortunately, at least in the case of Kepler, the survey is just not that sensitive to stars this faint, so it's really not great at studying M dwarfs, but that hasn't stopped us before. One of the most famous demographic studies to date is the work of Dressig and Charbonneau, which took place back in 2015 while Kepler was still ongoing. And they used what M dwarf sample they had available at the time to derive an occurrence estimate of about 24%. So again, 1 in 4 stars, but this time M dwarf stars, could host an Earth-sized planet in its habitable zone. Well, 2015 was kind of a long time ago, long enough that I was actually still in high school. But there's a more scientifically relevant reason why it's a long time ago, and that's that Kepler has basically completely transformed since then. We got new information from the Gaia mission, which helped to revise the properties of Kepler's stars and planets, and the transformations were kind of a big deal. To illustrate this change, here is the original properties of those Kepler M dwarfs that we had back in 2015. Everything is on the right side of this plot, meaning that it's less than 4,000 Kelvin by definition of what an M dwarf is here. I'll now plot the Gaia updated version of those properties, and everything moves up and to the left, meaning stars were larger and hotter than what we used to think they were. But the real problem is that more than half of the stars we used to think were M dwarfs are actually not M dwarfs. They're more like mid to late K-type stars. They're just a little bit too hot or a little bit too big. So this immediately got us worried, thinking, oh man, like if all the M dwarfs are gone with Kepler, how many planets are left in that sample? And the answer is like 40, which is a decent number, but it's not a ton. In this plot, I'm showing the vertical axis for planet radius, really zoomed in on Earth-sized planets. And the horizontal axis is now showing the installation or incident flux that these planets are receiving. Again, kind of a metric of how far away planets are from their stars. Anything on the right side of this plot is like farther away from their stars, and the habitable zone is also on the right. You may note that there's only one planet in there, and I should say that it's maybe a planet, as there's about a 40% chance that it could be a false positive. So those aren't great odds, and it got us worried that Kepler doesn't have a ton of information on M dwarfs, or at least not nearly as much as we used to think it was. So how does that affect Eta Earth? Well, as always, we're going to use what information we can to do some occurrence rate modeling, but know that we couldn't fit anything as complex as what I did in the first half of this talk because there's just so little information. There is one point in the habitable zone, but it's really uncertain because it's like maybe a planet. And as a result, any model that we try to fit to that is also going to have some really big uncertainties moving across the habitable zone. Unfortunately, that also translates to the occurrence rate estimates that we're going to derive from this model. So here is a selection of some Kepler M dwarf occurrence rates with our most recent estimate on the right side. Our median value is a little bit lower at around 14%, but I don't really want you to focus on that. The thing I really want to stress is that today's estimate is a lot more uncertain. as a consequence of Gaia taking away a lot of the stuff that we thought were M dwarfs, it meant that Kepler just doesn't have a ton of information. So from an observational perspective, Eta Earth is just not as well constrained as you might be used to thinking. These large uncertainties give rise to another unfortunate caveat that they're so large they kind of encapsulate the range of recent sun-like star estimates, which means that Kepler doesn't have any evidence saying that Eta Earth should be higher or lower for M dwarfs than it is for sun-like stars. Now, M dwarfs aren't necessarily a focus of something like the Habitable Worlds Observatory, but they are a big focus of something like the TESS mission, which is doing a wonderful job of finding lots and lots of small planets around nearby M dwarfs. If you are interested in small planet demographics, especially around mid to late M dwarfs, I really recommend checking out the work of Ment and Charbonneau from earlier last year. I'll also tease the K2 mission, which is Kepler's sort of secondary campaign that happened to pick up a decent number of small planets around M dwarfs. So we've joined forces with the scaling K2 team and are working to try and squeeze as much information out of that sample as we possibly can. That's everything that I had to talk about for the M dwarfs, but I'll stay on this slide to sort of set up a teaser for the next chapter of my dissertation. Kepler is great, but it has a lot of limitations. And some of those limitations are things that other surveys, other data sets, and sometimes even other detection methods are well suited to help address. So there is very much a market for combining information from Kepler with other demographic sources, and that is exactly what we have been cooking up. I don't have nearly enough time to introduce that today, so instead I'll set up a little teaser. If you happen to be the Exoplanets 5 meeting next month, you can swing by my poster on Tuesday to catch a very preliminary result of this. And if you can't, keep an eye on my website, which is linked at the bottom of the slides, or toss me an email, and I would be very happy to talk about that with you. But for now, I should probably stop talking. So I'll throw up this summary slide, and I would be thrilled to take any questions.
All right. Thanks so much, Galen. That was excellent. All right. Any questions? You can either throw some in the chat or use the hand raise tool, which is under the reactions button. All right. I already see one question. Lisa, go ahead and ask your question.
Hi, Galen. Great talk. Thank you so much for the work. I was wondering, when you move these stars into the K bracket with the new Gaia data, did that help? Can you introduce that in the sun-like star sample? Because you said that was FGK. So now you should have more. If there's less M star planets, now you should have more in the K bracket. Will that help?
Great question. When we started the sun-like work, we started with doing those Gaia updates. So I didn't introduce them until we started talking about the M dwarfs, but we knew that there were more stuff that we could use in the K dwarf sample. So those were very much included in our 2022 study.
All right. Any other questions? Again, hand raise tool or in the chat. Can you give more of a teaser? Since I know I'm not going to Expo 5. Can you give more of a teaser about what your poster will entail there?
Yeah, so we have been working on setting up a demographic modeling tool that works across detection methods, which is really hard to do, but we've maybe finally pulled it off. And so the poster includes a plot of Kepler plus radial velocity giant planet occurrence rates, sort of building off some work of, for example, Rachel Fernandez a couple of years ago, looking at sort of how you can supplement Kepler's short period limitations with stuff that goes farther out. And that's what's on the poster, but we're currently working on adding information from like microlensing and eventually direct imaging.
Awesome. Thanks for the preview. Look forward to seeing the tool. All right.